Today, we're really getting into the heart of your computer. We're talking about computer architecture.
Yeah, the blueprint, essentially, how everything inside that box actually fits together and talks to each other.
Exactly. Think of it like peeling back the case, looking at how all those, bits of hardware are organized.
It's fundamental stuff.
It really is. And our mission today is pretty straightforward. We want to demystify this. If you're new to computer science, or maybe just curious about how your phone or laptop works.
Understanding this base layer is, well, crucial. It underpins everything else.
Totally. So we'll be exploring the big players, the bus, the CPU, RAM, and those input-output things. Keyboards, screens, hard drives.
All the main components.
Right. So let's maybe start with an analogy. Imagine your computer isn't one big thing, but more like a company.
Okay, I like that.
Different departments, each with its own job, but they all have to work together, communicate constantly. And according to Dr. Reza Abdali's work, the main departments we're looking at are the bus,
The communication system,
the CPU, the central processing unit,
the brain,
RAM, random access memory,
short-term memory, the workspace.
and then various input-output devices, like we said, keyboard, display, hard disk, that sort of thing.
And it's not just that they exist, right? It's how they depend on each other. That interaction is the architecture.
That's a really key point. It's not just a list of parts, it's the collaboration.
Without that blueprint, that planned interaction, you just have, well, a jumble of electronics that wouldn't do anything.
Okay, so if it's all about interaction,
Yeah.
how do they talk? How does the CPU know what I typed on the keyboard?
Ah, good question. That brings us right to the bus.
The communication highway? Or maybe the central announcement system?
Both kind of work. The simplest definition is just. It's a shared way for lots of different devices to communicate without needing, a direct wire between every single pair.
Right, that would be a mess.
Exactly. And while we often say highway, the sources suggest thinking of it more like a shared basket. Everything gets dropped in the basket.
A shared basket?
Yeah.
Okay. But wait, if everyone throws their messages in at once,
Chaos. Right. That's the challenge with any shared resource. How do you manage it?
so how does it work? Let's use your example.
Right.
The CPU wants to know if I typed something.
Okay. Step one. The CPU puts a message, basically, keyboard, you got anything new? Onto the bus. Puts it in the basket.
Okay.
Now, here's a really neat part. Every other device hooked up to that bus, they're constantly listening. They act like state machines, always checking. Is that message for me? Is that message for me?
So they're all eavesdropping, basically.
In a way, yeah, constant vigilance. So when the CPU puts that keyboard message out.
The keyboard sees its name, essentially, and grabs the message. Everyone else just ignores it.
Precisely.
And if I did type something, say the letter A.
Then the keyboard puts its own message back onto the bus. Something like CPU, yep, user typed A, back into the basket.
And finally, the CPU checks the bus again, sees the reply, and knows I typed A.
And that's the core loop. What's amazing is how efficient this is, even though it's shared. There are clever rules, protocols, managing who gets to use the basket when, preventing those collisions.
It avoids that spaghetti junction of wires you'd need otherwise. It's actually pretty smart.
It really is a very elegant solution.
Okay, so that's communication sorted. But the computer needs a place to hold the stuff it's working on right now. The data, the program instructions.
Which leads us neatly to RAM, random access memory.
The main memory. The computer's temporary workspace.
Yeah,
I always think of it like my desk when I'm in the middle of a project.
that's a great analogy.
You pull out the files you need, the tools, you work with them, and you put them away. RAM's like that desk for the CPU.
Exactly. And how it stores things is important too. It uses addresses. Think of it like a huge street with numbered houses. Every byte of data, every instruction gets its own unique address.
So the CPU can just say, I need the data from address 1024.
Precisely. And it can access any address directly, hence the random access part. But it's volatile. That's crucial. Meaning when the power goes off, poof, everything in RAM disappears, like clearing your desk completely.
Right, which is why we have hard drives and SSDs for permanent storage. RAM's just for the active stuff.
Exactly. That's the trade-off for its speed.
And this tech has evolved too, right? I remember different types of RAM.
Oh, definitely. Before the early 90s, it was mostly DRAM, dynamic RAM. Then came SDRAM, synchronous DRAM, which was a big step up.
And now we have DDR SDRAM, double data rate. That's pretty much standard today, isn't it? DDR4, DDR5?
Yep. Those sticks you plug into the RAM slots on the motherboard. Faster RAM generally means a snappier system because the CPU isn't waiting as long for data.
So tying it back, RAM is the CPU's fast, temporary scratch pad. Absolutely vital for performance.
It's the immediate workspace. Without fast RAM, the CPU would just be idling most of the time, waiting.
Okay, workspace covered, communication covered. Now, let's talk about the star of the show, the
Yeah.
boss, the brain, the CPU, central processing unit.
Its main job. Just one thing, really, but it's everything. Executing instructions. That's its entire purpose. Without the CPU running instructions, nothing happens. It's just silicon.
So let's peek inside the CPU itself. It's not just one block, is it? There are parts within the brain.
Right. Key components working together at incredible speed.
Like memory registers. What are those?
Think of them as tiny, super fast storage spots right inside the CPU, even faster than RAM, when the CPU needs to do a quick calculation.
It pulls the numbers from RAM into these registers.
Exactly. Operates on them there, gets the result, and maybe stores it back to RAM or keeps it in a register for the next step. They're like little scratch pads for immediate use.
Got it. Then there's the ALU, arithmetic logic unit.
Yep, that's the calculator part. It does the actual math addition, subtraction, and the logic, like comparing if two numbers are equal or not. The number cruncher.
Okay.
And the instruction register.
That holds the specific instruction the CPU is working on right now, like the current command it needs to carry out.
And the instruction pointer, or IP. That sounds important. Oh, it's vital. The instruction pointer, sometimes called the program counter, always holds the memory address in RAM of the next instruction the CPU needs to fetch.
So it's like a bookmark, telling the CPU where to go next in the program.
That's a perfect way to put it. It constantly points to the next task.
So you've got these super fast registers, the ALU doing the math, the register holding the current job, and the pointer saying what's next.
But who's telling them all what to do and when? Who's conducting this orchestra?
There must be a conductor.
There is. And it's arguably the most fundamental piece of the puzzle. The control unit.
The maestro. Inside the CPU.
Right inside the CPU. It's a complex state machine, and its job is to manage that whole process, that endless cycle of fetching and executing.
It runs the whole show.
It absolutely does. It directs the traffic, telling the ALU when to calculate, telling the registers when to store data, fetching the next instruction based on the instruction pointer. It orchestrates everything based on a very simple, very powerful cycle.
The fetch, execute, repeat cycle. I've heard of that.
That's the one. It's the heartbeat of the computer. Let's break it down.
Okay, step one.
Fetch. The control unit looks at the instruction pointer, IP, to get the memory address of the next instruction. It goes to RAM, grabs that instruction,
Fetches it.
and pulls it back into the CPU, placing it in that instruction register.
Got it. Step two.
Execute. The control unit looks at the instruction it just fetched. It decodes, it figures out what it means. Remember, there's a limited set of commands the CPU understands.
Like add, load, sort.
Exactly. Based on that command, the control unit tells the other parts what to do. It might tell the ALU to add the contents of two registers, or tell a register to load data from a specific RAM address. It carries out the instruction.
Makes sense. And step three.
Repeat, or rather, prepare to repeat. After the instruction is executed, the control unit usually just bumps up the instruction pointer IP to point to the next instruction in sequence in RAM.
Moves the bookmark forward.
Right. And then it loops right back to step one, fetch. It fetches the instruction the IP is now pointing to, executes it, increments the IP, fetches the next one.
And just keeps going. Over and over.
Billions of times a second in modern CPUs. That simple loop, fetch, execute, update pointer, repeat is what makes everything happen.
Wow.
Now, modern CPUs do incredibly clever things to speed this up, like pipelining, starting to fetch the next instruction while the current one is still executing, or speculative execution, guessing what comes next.
So they overlap the steps.
Exactly. But it's all built on that fundamental fetch-execute cycle. It's mind-bogglingly fast, but the core logic is that simple loop managed by the control unit.
That's actually incredible. That simple loop drives everything from browsing the web to playing a complex game.
It really does.
Okay, so we got the core. Bus for communication, RAM for workspace, CPU with its control unit, ALU, and registers running that fetch-execute cycle. But there are other bits on the motherboard. Right, things connecting these main parts.
Absolutely. Especially historically, we talked about the Northbridge and Southbridge.
Yeah, I remember those terms. What'd they do?
The Northbridge was typically the high-speed controller. It connected the CPU directly to the RAM and often the main graphics slot. Think fast connections.
Okay, the express lane and the Southbridge.
That handled, well, pretty much everything else, slower stuff. Input-output devices like USB ports, hard drive connections, audio, the standard PCI slots.
So one for speed, one for peripherals.
Kind of, but here's the thing, that distinction is blurry now. Modern CPUs, especially SoCs, system on chip, have integrated a lot of that Northbridge functionality, like the memory controller, right onto the CPU die itself.
Make it faster, less travel time for the data.
Exactly,
Yeah.
lower latency. And much of the Southbridge functionality is now often in a single chip called the Platform Controller Hub, PCH. So the terms North-South Bridge aren't as relevant for brand new systems, but the functions still exist.
Got it. So the rules are still there, just packaged differently. What about those slots for plugging things in, like graphics cards?
Right, the I/O device slots, they've changed a lot. We have the old, slow ISA slots.
Ancient history.
Pretty much. Then PCI became standard for a long time, then AGP showed up, specifically for graphics because they needed more speed.
And now it's all PCI Express, right? PCIe.
Mostly, yes. PCI Express was a huge leap. Instead of a shared bus like PCI, it uses dedicated point-to-point lanes. Think of it like giving a graphics card its own private highway to the CPU or PCH.
Which means much more data can flow much faster.
Precisely. It enabled the kind of high-performance graphics and fast storage like NVMe SSDs we see today.
Speaking of storage, the connectors for hard drives and SSDs have changed too.
Definitely. That was traditionally Southbridge territory. We went from parallel ATA, PATA, which itself evolved from IDE.
Those wide ribbon cables.
Oh, yeah. And there was SCSI for servers and high-end stuff. But now it's overwhelmingly serial ATA.
SATA, much smaller cables. Why the switch from parallel to serial? Seems counterintuitive.
It does, but at high speeds, keeping all those parallel wires perfectly timed becomes really difficult. You get interference. Serial, with fewer wires but running much faster, turned out to be more reliable and ultimately higher bandwidth for storage.
Interesting. And of course, we have USB headers on the board for all our USB ports.
Connected via the PCH, typically.
Yep. And finally, the big one, the CPU socket itself, where the brain plugs in.
Right. Lots of different physical socket types over the years, specific to different generations of CPUs from Intel or AMD. But maybe more important than the physical socket is the language the CPU understands.
The instruction set architecture.
Yes,
ISA.
exactly. That defines the set of commands the CPU knows how to execute. The dominant one today, for desktops and laptops anyway, is by 8664.
Which came from AMD, building on the original Intel by 86.
That's the one. It's the common language that allows software compiled for by 8664 to run on CPUs from different makers, which is huge for compatibility.
So it all ties together. Let's recap maybe.
What idea?
Okay, so your computer, deep down, is this system of parts. They all talk over the bus, that shared communication basket.
Right.
RAM is the fast, temporary workspace, holding the active programs and data at specific addresses, but it's volatile.
Gone when the power's off.
Then the CPU is the engine. Inside it, the control unit runs the show.
Orchestrating that constant fetch, execute, repeat cycle.
Using the ALU for math and logic, and the super-fast registers for immediate work, all guided by the instruction pointer.
And connected through things like PCI Express slots and SATA ports, managed by logic, now mostly integrated into the CPU and PCH.
It's complex, but also kind of elegant when you break it down.
It really is. And understanding that fundamental architecture, that flow of instructions and data is just, it's the first step. If you want to really get how computers work, this is ground zero.
Absolutely. Whether you're coding, troubleshooting, or just curious.
It's the foundation.
Well, that's our deep dive into computer architecture for today. And here's something to maybe think about as you use your devices. All that incredible stuff they do, video editing, complex simulations, instant communication across the globe. It all boils down to that incredibly simple, relentless fetch, execute, repeat loop, running billions of times a second. How does that basic cycle build up to create the digital world we experience?
That's a fascinating question. The layers of abstraction built on top are just staggering.
It really is something. We hope this gave you a clearer picture of the magic happening inside the box. Thanks for joining us.
Keep exploring.